newtons? It's up here. And it's upside down too. Yep. 2.5? Yes.
I have 3.
Oh, here's some great predictions. Okay, who did I get the yes explanations from? Okay. So why did you predict 2.5?
This is your gear.
Oh,
So the middle one, you'd have your gear, and one moving your gear. Very good. So if this leader's turning this way, okay, so at the other side,
is that yet?
flip that arrow.
How's it going, guys? You doing good? Yeah. Okay, good. How much force? You feel how much force it takes to move that load. Then once everyone's had a turn, we'll build a pulley, then we'll pull the same load, and see if we can feel any difference in the force we need to move it. So what are we going to use as a load? Us? You want to be my first load?
Oh! Stop the camera! Stop the camera! Stop the camera!
See?
Oh no, you're gonna kill me!
Can you sit cross-legged? Then you're going to hold on like that, okay? Okay, girls, come on down here.
Uh-oh.
No, just leave her up for a second. All you do is pull? No, not yet. Yeah, all you do. That's all you have to do.
So we have to pull this guy?
Okay, come here. Okay, so let me just before you start. So, it's heavier, right? You're going to sit there and you're going to be like that load in there, that weight in there. So the weights don't move. So don't lean back, don't move your arms or anything. Just bang. Now the way you're going to pull is you're going to keep your feet in one place and you're just going to pull one hand over the other.
Like that?
Yeah, and I'll put my foot there in case you start slipping, because sometimes these boys are slipping. Okay. You can start moving them now. Nice and gently, nice and gently. Yeah, Jeff, do it gently.
I can't do it now!
Okay, that's good.
He's too heavy!
So remember how much force you're taking. Okay, so Magda,
Stop the camera!
Magda, can you put that down on your lap, please? Yeah. Okay, so you're going to keep it nice and steady, remember. You're not going to move your arms. Okay, so one hand over the other.
Oh, I do.
There you go. Awesome.
Make us that.
That's good. Nice and steady like that. Steady, okay? Okay, go. Okay, so you're strong.
But you can't pull me.
Awesome. Good. And the groove is formed from the tennis balls, and this is all it is. This is a pulley. Okay. Just like this. So you're my first load, have you? So come back here.
Let's sit on the mat.
Yep, put back here.
Oh! Please don't use me.
I'll do
The
that.
seat. No, I need that.
Please do that.
Do it one hand over the other. Come on, you got it. You got him. Okay. That's good. The other, okay, nice and steady. Okay. Magda, can you put your hands right beside the tennis balls, right up against them? Yeah. Okay. That way it doesn't slide. Okay. Was it easier? Design a gear train. So remember I said a gear train is a series of gears. So you can use this, you don't have to stand up and I don't know where you want to move it. But you can design a gear train. Now, I don't want you guys making all your own. I want to make again one big gear train so that when you turn the lever here, all you can bring something on top and make it spin. First one is skirt, add other things to the side. Try to do every design you want. Again, I want to see
Your wheels left to previous passes, and you have 2 sides here. Yes, and then you're going to have one and another gear with the camera. Right, so you're going to check your 3 bases.
Where is the effort in this picture? Okay, I think that's pretty straightforward. This is a pretty good dimension. Give a pencil. Use a pencil. Because if you make a mistake.
You have one thing here. Twist the belt. Twist the belt. You can twist it. Twist it and see if it works.
You're in the middle. You're in the middle.
Better.
So you twist the belt. You notice how it's now moving in the opposite direction. direction. Very good. You see this, how I showed you how this gear train?
We're working.
Okay, ready? See? Is it easier or is it hard? It's harder, remember? Show up is harder. Now, let's try this one here. Okay, put this one down.
Each of the holes in that little middle disc makes a different design, and if you look, I can switch. So now I'll pick one in closer. I kept my internal gear in place, and now it makes a different design. So you guys can try that. So this is my frame.
Are you even recording?
Show your internal gears. Okay, and use my lens, okay? The other, use your pencil, your paper, not on your paper.
You can look it out.
Now we go.
Done whenever something is moved over a distance. So Newton determined that work be expressed as work equals force times distance. So how much force you apply over how much distance. So let's see if we can, if you just put that up for me. We're going to try something. So Nicholas, I need some help from you please. You can stand up. I'm going to get you to go over to that wall, and I'm going to get you to push really hard and push that wall into the next room, okay? Push it. Okay, thank you. That's good. Okay, good work. Okay, and Sarah, I need you to come up here, and you can do some work too. So if you could lift that weight up and put it back on the desk for me. Lift that up. Excellent, thank you. You can have a seat. So now we want to see how much work was done, because Nicholas, we sent Nicholas over to push the wall, and we know that work equals force times distance. Now he probably put a lot of force into trying to move that wall, didn't he? So we're going to say, we're just going to pick a number, and we're going to say 250 newtons of force he used. So he did, we're trying to figure out how much work he did. How much distance did he move the wall? How much did he move that wall, Andreas? 0. So what's any number times 0? 0. Right. So Nicholas didn't do any work. He tried, he applied a lot of force, but Nicholas didn't do any work. Now Sarah, so for Sarah, we have work equals force times distance. Which force do you think you had to use? Was it a lot of force you had to use, or not too much? Probably not as much as Nicholas, was it? So then there's the column for predictions that we're going to use, and then the column for actual force. And you'll notice that newtons is in brackets, because we're going to measure force in newtons. And newtons comes from the name of good old Sir Isaac Newton. That's how we measure force. And we need a measuring device for that. It's called a spring scale. It's a very simple looking device. You can see the spring here. When you attach a load, the spring expands. And there's a numeric scale on the side, and it just moves down to the appropriate result, measuring